To me, writing the book actually was this sort of double-edged sword where it was full of inspiration and there's these wonderful stories of discovery and brilliance. But also it was full of outrage for me, and I think readers will feel that outrage too, because these stories should be known and these women should be household names, and they aren't.
Welcome to a new episode of the PAM Talks. The PAM Talks is a student-led podcast showcasing the voices of researchers who are a part of traditionally underrepresented groups in physics and astronomy. Each episode, we interview a new physics and astronomy mentor, exploring the universe through the lens of diversity. My name is Gabby, and I am a master's student in physics at the University of British Columbia. Today, I am interviewing Dr. Shohini Ghose. Shohini is a professor of physics and computer science at Wilfrid Laurier University, working in quantum physics research, and is the chief technology officer for the Quantum Algorithms Institute. Specifically, she studies quantum superposition and entanglement and their applications to computing and information processing. She is also a leader in STEM equity, diversity, and inclusion initiatives in Canada, and is an NSERC chair for women in science and engineering and the research and programs director for the Laurier Center for Women in Science. We will be learning about what quantum computing developments mean for our world today, and about the work Shohini is doing to pave the way for the next generation of women in physics while honoring those that came before us. Shohini, thank you so much for joining me today. It is an absolute honor to be able to be interviewing you.
Thank you for having me. I'm looking forward to our conversation.
Shohini, I know you have been a leader in multiple research areas in the quantum sector. Could you start off by explaining to our listeners a bit about where your current research focus lies?
Sure. Yes, as you mentioned, I'm a quantum physicist by training. That's what my PhD focused on. And actually, the field is much bigger than what is currently getting a lot of attention, which is quantum computing and, this all of its potential for hacking everybody's passwords and things like this, which of course is very, very important. But being a theoretical physicist, I've been in the field for a while now, even before the quantum computing revolution. So as a fundamental theoretical physicist, my goal is always to explore what we call, the laws of quantum mechanics. And why is it that these laws that apply to particles like photons and electrons are very different from the laws that seem to govern our macroscopic world of you and me and objects that are much, much larger than electrons and photons. So my research is about trying to probe that and understand what is quantum superposition, what is quantum entanglement, and by trying to understand what you can do with them in terms of information processing, computing, or cybersecurity, that tells us a little bit about their power, but it also tells us what's that difference between our current computing versus quantum computing. And therefore, that identifies what these laws really imply about this universe that we live in.
So to me, I hear that and I think you do everything.
No.
It definitely seems like quite a lot. I think that's one of the things that I find quite exciting about theoretical physics is you ask someone what they do and they never just say, well, I'm trying to develop this one thing. It's, well, I'm trying to understand really the core of everything we're talking about, and you can take my work and run with it. And I always enjoy talking to theorists for that aspect of it. So when we talk about quantum computing, could you define for us what the difference is between a quantum computer and a classical computer that I'm working on right now?
That's a great question. So a quantum computer is going to be nothing like your current classical computer, your laptops, even supercomputers, because it's a completely different framework for computing itself. What I mean by that is we know that all of our calculations, really, they boil down to zeros and ones, binary digits, which we call bits. And everything is just combinations of zeros and ones. So inside your laptop or even a supercomputer, all that's happening is that there's these switches that are, switching between 0 and 1. And these are just currents that are, your transistor is controlling all of these sequences of switches, and each sequence is a particular, calculation that your computer is doing. So that's very easy, and it's also really convenient because everything can be done just through that kind of binary logic. It's universal. So a quantum computer is also a universal machine, but it's actually a broader approach to computing, meaning the binary approach of bits and switching between zeros and ones is a subset of this larger framework of computing itself, where instead of just restricting yourself to 0 and 1 and just that switch, we allow more space between the 0 and 1, if you like, where you can be in some kind of a what we call a superposition of 0 and 1, where there's some probability of 0 and a probability of 1, which doesn't sound very precise, but actually it's good to think of it as an additional knob, where instead of just flipping a switch up or down, you can turn a dial from all the way between 0 and 1 in such a way that you have more precision control and can do certain types of calculations better. Just like you can do some things with a dial that you cannot do with a switch. So a quantum computer is kind of like that. It's a completely different technology and it'll take many years to develop. But when it is rolled out as a commercially large-scale device, it will be able to do certain calculations that can take our current computers, even supercomputers, the age of the universe, perhaps, to calculate. But a quantum computer may have the ability to do that calculation much, much faster because it has all these extra ways to compute. And so that's why it's a very exciting new field.
So quantum computing is definitely a hot topic right now. Something that I'm interested in is our encryption abilities. So we hear about things like protecting national security with quantum encryption, or just even keeping my own bank details safe. So what benefits does quantum encryption allow over just the standard security we have on our computers?
Yeah, so the current security is based on actually a lot of hard math problems. So the reason, for example, our passwords are safe when we send it, on these public channels is because we're not, of course, sending our passwords openly. They are being encrypted using some kind of process, which basically requires doing some mathematics. And in order for it to be decrypted, the bank knows how to undo the mathematics. And if somebody wants to hack into your password, which is encrypted, then they would have to solve that hard math problem as well in order to see your actual password. And these days, the hard math problem that is used, it doesn't sound very hard. It's just factoring of large numbers. So things like, 15 being 3 times 5, but that's, of course, very easy. But if you go to, 200-digit numbers, for example, those turn out to be computationally very, very difficult. And in fact, the difficulty grows exponentially with the size of your number. But the problem is that we now know that if in the future we have quantum computers, then there is a way to crack that particular math problem of factoring, which means that's not going to protect us. If we're going to use factoring to encrypt, then in the future, all of our passwords and our secret information will not be so secret anymore. Hence, we have to find a different way to keep all of our data safe. One way is to say, well, let's not use factoring. Let's go to a different math problem. And in fact, that is what's being done now. They're developing new kinds of encryption standards, which are essentially a shift to new types of math problems. The problem there, though, is that we don't know for sure. If it's a math problem, there may be a solution. So we would have to actually find a math problem that we can prove can never, ever be solved efficiently. And we don't really know how to do that. So there's another way, therefore, to attack the problem and say, well, let's not base encryption on math problem. Let's base it on the laws of physics. And in this case, quantum physics. So what if we could encrypt information by using these quantum properties of superposition and entanglement? So the idea is you hide your information using these quantum approaches and quantum characteristics. So if a hacker wants to actually read your data, they would have to hack the laws of physics rather than solve a math problem. They have to change quantum superposition and entanglement. And that's, I think you would agree, is a bit harder. So that's really what is the potential benefit that quantum can offer. If we can make that kind of encryption work, then we could shift over and go to that method of encryption. And that is going to be safe because it's not about math problems. So even if in the future some very powerful computer was built, or even a quantum computer, it would still obey the laws of physics. So it's not like it would change the laws of physics and then hack that quantum encryption. So that would be a much more powerful type of encryption, but there's practical challenges because to create that kind of encryption standard would require decades of effort. And even if it does succeed, the question is who would have access to that kind of encryption, and would all of us have the same access? And if we did, is that a good thing or a bad thing? Because then we wouldn't know anything about what's happening or who's doing what anywhere in the world.
That's an excellent point. I never really thought about it like that. When I hear about the improved encryption abilities due to quantum computing, I always think, that's wonderful. My bank is now better protected. But I never think about sometimes needing to hack someone for the greater good. So that's a really fascinating perspective.
Right? It's yeah. I think whenever you take any kind of technology to its, extreme points, you have to think, well, is that really where we want to go or not? And it's hard to predict, right? How that'll be used. I mean, what if, the so-called bad guys get to use the technology? Is that really a good thing or a bad thing? Who knows?
Yeah, certainly. Do you think it is practical that one day we could be operating on this quantum internet? Say we've sorted out the bad guy problem and now it is just a matter of practicality?
I think the bad guy problem is a much more complicated problem than perhaps the technology problem because it involves humans, and I'm no expert on, things like policies and international cooperation, which is what it will take, right? It will take some level of international agreements and governance. When we talk about anything to do with data security and global systems and things like this, there's geopolitics involved. So that's a very, very complex problem. People are already addressing it. On the technology side, different countries are at different stages in developing and investing in this kind of quantum encryption standards. All of the efforts, I would say, have been focused in the global north. So we're already starting to see what we call a quantum digital divide, where certain countries perhaps will not have the same access as others when this technology is rolled out. So that's something, again, we'll have to tackle to really figure out how to build something that's fair and equitable as well.
Yeah, that's really fascinating thing to think about, and it really how science and policy intersect at this kind of research. And even as a scientist that is not involved in that kind of policy yourself, I'm sure that's definitely something that at least lingers in the back of your mind. Although I do know that you are very involved in other sorts of policy, and I feel like the involvement here is quite a natural connection to all of the EDI work that you've done. And I know that you are definitely a champion for EDI in Canada, and have done a lot of work in that respect, from the NSERC Chair for Women in Science and Engineering to your work with the Laurier Center for Women in Science. I'm curious to know how the goals of the organization have grown or shifted since its inception.
Well, our goal has always been to not exist, actually, because as long as we need to exist, it means that there's an issue with having full, equity and diversity and inclusion in the science community. So I think that I, like many of us who work in this field, are not doing it because somehow it's, something that we choose as a career goal. No, it's quite the opposite. Those of us who build careers, face challenges, realize that there are all kinds of structural issues, and then decide we need to fix it. And, it's kind of like any kind of problem that you fix, right? Let's say you have a healthcare issue. You work to fix it because you don't want to have it forever. So once it's fixed, you can move on. For me, this work with the center is exactly in that vein, as in, this is not a center that should exist. So as long as we keep that as the focus, all of our goals are very clear. When we get to a point where there is full representation in science, when access is fair and equitable, when career paths are fair and inclusive, then we would be more than happy to shut down. So that is our goal, and that has not actually changed.
Oh no, certainly. And I know there's so much progress to be done in science around the world. My question, what progress have you been able to see in your term as director? Or do you think that the progress that you're able to see happens over a much larger timescale?
No, absolutely. The progress has been slow, but there's definitely been progress over the last decade that our center has existed. The biggest progress, I would say, based on, when we first started 10 years ago and now, is that this has become a national conversation, and not just in Canada. This is a conversation that is growing elsewhere around the world. And to be fair, the conversation is not like it started just 10 years ago when we started the center. There's been all kinds of initiatives to try to promote the number of women participating in science, particularly in areas like physics and computer science and engineering, to improve those numbers. There's been lots of initiatives back from since the 80s. In fact, even the NSERC chair program that I'm a part of, that was something that was initiated in the 80s. So we've had these kinds of conversations and awareness and ongoing efforts for quite a while, but the numbers have not reflected all those efforts as yet, I would say. So progress is slow. What I think has improved, as I said, is that we have shifted from thinking about this as individual activities where, we run summer camps and outreach and mentor girls and young students. We're shifting now to try to think of this as a systems issue and to look at it structurally and understand what are the processes and structures and barriers that currently exist in our institutions that have to be dismantled or changed. So an example is the NSERC chair program, and NSERC in general, which is of course the largest funding source for science research in Canada from the federal government. NSERC has now built into its funding applications some kinds of policies and criteria that promotes fairness and EDI in research and training. So that's an example of an improvement where we are now trying to address this from that systems level and the processes for getting grants and building research programs, rather than only focusing on mentoring and what I call, fix the girls kind of approach, where there's lots of training and camps and professional development and so on. That to me is perhaps not the right way, and we've seen that they haven't had as much impact on the numbers and environment. So we really do have to focus more on these structural barriers, and we have been moving towards that more and more so in Canada, at least. So that's good.
Yeah, I'm so happy that we're seeing this shift in Canada, because I totally agree with you about those the one-off fix the girls initiatives. Yeah, they're really fun for the day, but I feel like afterwards you lose that connection kind of thing. So seeing these more long-term funding programs where they'll help support you throughout your degree program it feels so much more rewarding as a participant in those programs.
Yeah, and I think we have to think beyond this approach of supporting women, because as I was saying about the center, it's not going to really work if we're in the mode of either supporting women or fixing, women. So we have to get to that point where, just like we celebrate men who are doing great work in science, we celebrate women. We don't start with the deficit model, which requires support. We start with the assumption of really fairness and equal access and opportunity, such that when there is success, we celebrate it for the scientific success, because we know that it is built on a level playing field. So that's where I hope we can ideally reach. But I think we still, of course, are in the mode of trying to do the supporting, which I think is important to do because we're not in a fair system as yet. So needing that extra support and corrective measures and increased sorts of mentoring and so on is so that we can adapt to a system that is not ideal.
Yes.
So I think that's an important piece that we have to keep in mind.
I think that is an excellent point. That's really one of the goals of this podcast as well, to just really highlight the accomplishments of these women as scientists. Like you are a scientist first when we're talking to you here, and that's what we want to highlight in this series. So, and you've also been leading this kind of push and this work yourself with your book, highlighting the stories of historical women in science and sharing their stories as an accomplished and amazing scientist and all of the work that they've done, even despite them being in an environment that didn't always give them a platform to do that. So after doing the research and learning about all of these phenomenal women, does one really jump out at you whose story was the most fascinating or the most motivating to hear?
Um, It's hard to pick because actually to write the book, I already had to pick the list of women that I ended up including in the book were already basically what I call my short list, I guess, because there were lots more that I didn't want to write about. These were sort of the top women whose stories I really wanted to tell. But that being said, I will say that there's a couple there that if I absolutely had to choose, I would pick. One of them is Bibha Chaudhary, who is a Bengali physicist who did amazing work in particle physics back during the war, during Second World War in India. And the reason she's special to me personally is because I am Bengali too, and I grew up in Kolkata, which is the city where she also was born and raised. But when I was a student in Kolkata, I never heard her name. It's not like she's a big name even there. She's not in any of our physics textbook, although she was involved in the discovery of two fundamental particles in nature, the pion and the neutrino. And in fact, her method to first detect the pion, she couldn't confirm her discovery because, again, it was during the war. She didn't have resources to get better photographic plates that she needed to have better resolution. So she did publish her data, but she wasn't able to confirm that this really was a new particle that she had detected. And then her technique was used by a British physicist, Cecil Powell, after the war in the UK. And he was able to definitively identify this new particle, the pion, and he won the Nobel Prize for it. But she, of course, did not get the recognition she deserved. But she had an amazing career. She was brilliant. She was passionate about physics and pursued that back in that kind of an environment when India was actually under British rule. And she still had this wonderful career, did what she loved doing. With or without the recognition, it didn't matter. One of the reasons I wanted to include her story in the book was that I hope more students get to read about her. And another woman that personally I felt a connection to was Cecilia Payne-Gaposchkin, because she was actually an astronomer working at Harvard Observatory. She was the first student to do a PhD at Harvard Observatory. And her PhD work involved actually applying the laws of quantum theory to try to understand the spectrum, which is basically the light collected from the stars, and try to figure out what the stars are made of. And this was back in the early 1900s when quantum theory was, a new theory. Not a lot of people had enough expertise back then to really apply it to this kind of real world problem. She built on an Indian physicist's work, this other Indian physicist named Meghnad Saha. And she took his work and his equations and was able to apply it to figure out that all of these different star spectra, these recorded plates of all the light collected from the star, she was able to analyze them all and find this amazing pattern that even though they all look very different, they are all made up of hydrogen and helium. So this was this big, huge universal result. And it was so radical that she had to add a line in her thesis saying it may be wrong. But she was, of course, eventually proved right. And her work was just so far ahead of its time. She was this incredible, brilliant thinker and in quantum theory. So she is one of these early sort of trailblazers in quantum physics. And yet, she's not in any quantum physics textbook, even today. And being a quantum physics student through my PhD and all of that time, also, I never saw her name in any of my quantum textbooks. She is included now sometimes in some astronomy textbooks, but she's certainly not acknowledged as one of those early sort of leaders in quantum theory. So I feel like for me, it was really important to get to know about this incredible quantum physicist from, a century ago.
Yeah, like being able to do that work so long ago, especially with just the technology difference that they had then versus now, still being able to discover that kind of science is absolutely amazing.
Spectacular, isn't it?
I cannot wrap my head around how someone could be so talented to get that. It just blows my mind.
Right?
And yes, we need to be learning about these people.
Yeah. And to make such a huge discovery, not a small thing, right? This huge discovery about every star in the entire universe. How much more do you have to do to actually get recognition?
Really, and like doing that as a PhD student.
Yeah, so if you have that level of discovery under your belt and you're still not a household name,
No,
what's wrong with that picture, right?
that's like doing for your degree what you need to do in a lifetime for science.
Yeah, which most people will never do in their life, no matter how long you take.
Well, I think it's time to start releasing new editions of these textbooks.
I think so. And to me, writing the book actually was this sort of double-edged sword where it was full of inspiration and there's these wonderful stories of discovery and brilliance. But also it was full of outrage for me. And I think readers will feel that outrage too, because this level of discovery is still relatively unknown to the general public, which is why I wanted to write the book, because these stories should be known and these women should be household names and they aren't. So that was kind of frustrating, but on the other hand, I think it's important to feel that sense of frustration so that we can do better in the future.
Exactly. So one point I wanted to bring up is we've been talking a lot about women in your EDI work. And I know that Center for Women in Science, you of course are doing a lot of work specifically for women, but there are many other groups that are also still quite underrepresented in science. And a lot of those, you may share that identity with a different group, along with your identity of being a woman, like all these people, different people in science. So I was wondering, when you're doing these initiatives for women and evaluating their success, how does the lens of intersectionality come into that? And how does that play when you're deciding if your initiative was a success?
Well, you're right. There are many identities. Personally, I too have multiple axes that form who I am as a person. So, I'm a woman, but I'm also a person of color. I'm an immigrant to Canada. So there are many different aspects, and all of them bring different kinds of experiences and successes and privileges and challenges too. One thing to keep in mind is that intersectionality is about how multiple identities can combine to create perhaps new sets of challenges that are different. So there's some studies, for example, in physics. APS, I believe, has been involved in American Physical Society, which shows that if you look at the numbers of women who are getting PhDs in physics in the US at least, you see that it's been increasing over the last decade or so. And it looks like a nice straight line, upward sloping. But then when you start breaking it down also by race, then you see that then almost all of the increase is only white women. And all the other lines are completely flat. So that's what I mean by having this additional challenge of race combined with gender actually causes the situation to be different enough that you don't see the same consequences of all of these initiatives that have existed for so long and have changed the numbers, but not for everybody. And in fact, in a sense, they've made things worse because the gap between white women and everybody else has actually increased in physics. There's also, of course, an issue, though, on an individual level. For example, for me, if I face a challenge and maybe I'm in a meeting and I say something and I'm not heard, and this is a pretty common thing, and somebody else says it and they get heard. I don't know whether I'm not being heard because I'm a woman or whether because I'm not white or because of my accent. Who knows, right? It's not like at an individual level, you can separate out each part of your identity. So you do have to look at it holistically as well. So part of why we focused on the Center for Women in Science back when we started, intersectionality was not as much a part of the conversation. So when we started, just from practical reasons for getting funding and things like this, we focused on calling it the Center for Women in Science. But that being said, our initiatives and our approaches have always been about embedding inclusion into whatever is the context and the framework. Now, if it is truly an inclusive kind of approach, then it should be something that provides access and opportunity, not just for women, of course, but for anybody who wants the opportunity to contribute to whatever is the field we're looking at, or who feels that they have a voice and they are being heard and included. So that's kind of how we have approached all of our initiatives. It's not like we say, well, if you're not a woman, you can't be part of the whatever the club, I guess.
No, I really like that point you brought up about, well, just because we're focusing on women doesn't mean other people can't be part of the club. Because I think that's something that people often forget when they hear about all these different initiatives coming up for targeted groups. Having specific celebrations of women in science and having more women in science does not hurt others. It's bringing you more collaborators, it's bringing more talent into the pool. Celebrations of women in science lead to celebrations of everyone.
Absolutely. And this is not a zero-sum game that if you are trying to help one particular group, it's not at the cost of every other group, or it certainly doesn't imply that every other group is not important. It happens to be that we all have specific resources, specific lived experiences, specific expertise. So we need to bring those to the table, which doesn't mean everybody else's resources, privilege, and expertise is not also welcome. That's why it's important to keep in mind that it's not one or the other, it's one and the other.
Yes, it's about having more scientists overall. We are coming to the end of our time, so I want to take a minute and just really thank you for offering your perspective here and taking your time to share your science with everyone, share your accomplishments, and share the stories of the women in science that came before you.
Thank you so much. It's a pleasure to be here and discuss these very important issues and so many broad topics with you.
The PAM Talks gratefully acknowledges the support of the University of Calgary Graduate Students Association Quality Money Grant Program.